Good evening, ladies and gentlemen. Thank you very much for giving me voice. Today, I will talk about documentation, a key strategy for biohydrogen, synthesis and energy sustainability, and I am a journal of the Oxygen University. The work is by Power Engineering Division, Professor Harsha Dukar. The worldwide development has intensive to utilize waste, and in our case, to get carbon neutral energy to replace fossil fuels, then which have a serious negative impact on the environment. A carbon neutral energy source for the future biohydrogen stands out for its ability to produce clean energy, control waste, and contain a large amount of energy. Due to the abundance, low cost, and renewable nature of agriculture waste, the production of biohydrogen was getting more attention because it happened in ambient temperature, pressure, and along with the production of clean energy. It is also helpful in efficient disposal of organic waste, which creates several problems after degradation in the open environment. The production of biohydrogen through dark fermentation depended on various operational parameters like pH, organic loading rate, types of inoculum, retention time, nutrient types of grades, organic substrates, which greatly affects the yields of biohydrogen. This paper aimed to introduce the basic concept of dark fermentative biohydrogen production, its mechanism, affecting factors, and suitable feedstock, and to aware people of this clean energy production technology. The increase in the global population has resulted in a sharp increase in the demand for energy. This is due to the fact that all activities necessitate energy. The largest portion of the energy is derived from fossil resources, which are non-renewable fuels that require more time to replenish or return to their prior levels of efficiency. Although fossil fuel-based energy is less expensive than renewable energy sources, it has several serious drawbacks. Growing public awareness of the harm that fossil fuel consumption does to the environment has emerged in recent years. Fossil fuels are widely acknowledged to play a role in climate change, and their extraction and consumption are linked to the development of significant volumes of non-biodegradable garbage. These problems have increased the scientific community's interest in finding alternative renewable energy sources. one of the future's most distinct alternative fuels is regarded to be hydrogen in this situation. This gas is a cleaner and more effective alternative to ordinary fossil fuels, producing only water during combustion and having a high calorific value of 120 megajoules, over than twice that of conventional natural gas or petroleum. Currently, the majority of hydrogen produced worldwide, about 96%, is dependent on chemical generation that employ fossil fuels as the primary raw materials. Hydrogen must be generated via sustainable methods such as physical chemical procedures such as biomass gasification, water electrolysis, or solar thermochemical processes, or biochemical reactions in order to be considered as environmentally benign and renewable alternative. Biohydrogen can be a good clean energy source in place of blue hydrogen, white hydrogen, and aquamarine hydrogen, because over 220 billion tons of agriculture residues are generated each year due to intensive agriculture farming, which is one of the most plentiful renewable sources for manufacturing this green hydrogen. After being purified, biohydrogen can either be used effectively in fuel cell to create power or in industrial combustion engines for biomobility. It can be produced via thermochemical or biochemical routes. The majority of commercial hydrogen producing technologies are thermochemical in nature. However, due to the technological and environmental drawbacks, the production of hydrogen through thermochemical routes, high temperature and pressure requirements, which are helpful in increasing the cost of producing this clean hydrogen. Hence, currently researchers are focusing on biochemical routes for producing biohydrogen. Dark fermentation methodologies have been found to be the most effective among all biochemical routes due to the use of a wide variety of organic waste as feedstock, and they occur at ambient temperature, pressure, and absence of sunlight. These salient features of this technology make it more promising among all biochemical processes. An environmentally beneficial substitute for fossil fuels that can help with the need to reduce carbon emissions in the creation of biohydrogen by dark fermentation. Currently, more and more work is being put towards improving hydrogen generation using the encouraging strategy. Anaerobic fermentation, sometimes known as dark fermentation, is the process of utilizing facultative or strict anaerobic bacterial strains to break down organic carbon substrates in order to produce biohydrogen. Along with the production of hydrogen, some value-added co-products such as volatile fatty acids, ethanol-type organic solvent, and organic acids like lactate are produced in this technology. Generally, 1/3 parts of the glucose carbon content are broken down into carbon dioxide and hydrogen, with the remaining 2/3 portion becoming volatile fatty acids. These are all beneficial substances that are utilized by the chemical sector. Methanogens or substrate reducing can be created during acidolysis and is competitive to hydrogen production. Mesophilic Dawn states for consumers such as low pH and short hydraulic retention time. The cellular requirement to release electrons naturally results in the generation of hydrogen, which is invariably accompanied by the formation of alcohols and or volatile fatty acid. Acetate, formate, and butyrate are the main co-products produced most subsequently during fermentation of glucose. When acetic acid is a co-product, the stoichiometric outputs are 4 moles of hydrogen for every mole of glucose and 2 moles of hydrogen when butyric acid is formed. The hydrogen output is real life at between 10 to 20%, approximately 170 to 234 mole hydrogen per mole of glucose. Generate 4 mole of hydrogen. It generates adenophosphate and reduced form of nitroadenine nucleotide. Base of bacterial community condition is ultimately transformed into butyrate, acetate, or ethanol, but mostly butyrate, however lower hydrogen than acetate, which generates 4 molecules. Inoculum is crucial variable due to imbalance of efficiency of hydrogen. This is the stimulated by ferredoxin and reduced by pyruvate ferredoxin acetoreins. They contain, including Clostridium acetobalatic, Clostridium butyricum, and Clostridium bergerinsky. Clostridia are primarily found in dark fermentation, utilizing the case. Temperature is the mesophyll 35, thermophyll 55, or extra thermophyll below upper the 65, exogenic metabolic condition, pH in 5 and 6, subscriptors are more sugar, more simpler, better, but also can protein, nickel and iron and potassium are most important salt. Hydraulic retention time, partial pressure is between 0.5 and 0.07 of partial. Is most popular partial within media has been agitation, and loading organic load is therefore evaluated is necessary, should be taken. Pre-treatment is mostly by thermophilic as the best. So these are the most important things to be made. And hydrogen has some both powerful low best and low yield, and sometimes pressure and high pressure and pressure requirements for proper treatment of more complex material is quite cost. And this, but it's sometimes quite can help some cheap technology to help methane production. And this is what I wanted to say for today. Thank you very much for listening.